Alrighty, on this lesson here, we're going to be going over 7.6, which is inverse trig functions. All right, there is a lot of information regarding the domain and range and notation purposes. So I'm going to kind of like hit the highlights. The domain and range is very important when talking about inverses because the way the graphs of inverses of these trig functions are, um, there is only a certain range of answers. If it's outside that, there will be no answers to it. So let's go right into it. So for notation purposes, sine with the -1 there represents inverse. This is not the inverse. All right. So sine inverse here would be, let's take the original notation. So we'll break this up in different colors. So we'll take sine x and we'll say, let's do this a little bit better. Make sure it's nice and organized for you. So here's our domain. And here is our, we'll put it way out here. Not gonna be that big, but some are. And there's our range. So for the regular sine of x, what we have seen is that for a certain period, we can actually go from 0 to 2 pi. For the sake of an inverse, we're only going to look at the domain of -pi halves, comma, pi halves, which will go from -1 to 1. So that graph, let's do that in orange as well. There's -pi halves, and here's pi halves. So at -pi halves, it is actually about right here, and at pi halves, it's about right here. And if give or take, not like a straight line, but something like this right there. If I was to curve this up or curve this down, using what we've learned in previous sections, this would then fail the horizontal line test and therefore not have an inverse. So we can actually modify the domain so that this part will have an inverse. So for sine x, this right here will have an inverse. So a couple things to think about on the unit circle. Sine x inverse will only have an answer in quadrant 1 and quadrant 4. So if it falls in quadrant 2 or 3, it will not have an answer. And that will make more sense when we look at it. So with that said, so sine inverse, remember inverses back in a previous section, you just switch the domain and range. So now the domain is -1 to 1, and the range is -pi halves to pi halves. I could have probably gave myself way more room now that I'm doing this on the board rather than on the paper. But now what's going to happen is now this is -1 and this is 1. And now this is pi halves and this is -pi halves. So therefore it kind of goes a little bit like this. Same concept. More of a curvy. I'm not the best artist there, but there you go right there. So therefore it would be a inverse. And again, that would be falling in quadrant 1 and 4 on the unit circle purposes. And we'll get to that bridge when we cross it. All right, let's look at cosine then. So cosine x, we're going to do the same thing. We're going to restrict its domain, but this time cosine's domain will be restricted from 0 to pi. Now you might be asking, why do we change the domain of this guy? Well, let's look at this graphically, and I really should just move this over at this point. But hopefully you can follow with the color code. For cosine, if I start at -1, so remember this is 1, this is -1, and then this would be about pi. right? If I go here at 0, I have a point, and then at pi, I would have negative points. So I would have an option that looks kind of like this. Had I gone right here, I would have had this situation going, and then I would have failed the vertical line test. So therefore, we had to shift our domain so that this section, or we could have technically made it from negative pi to 0, but we needed a section in which it wouldn't have overlapped. And so we went with 0 and 1. And this right here would represent quadrant 1 and quadrant 2. So on the unit circle, when you're looking for the answer, as long as it falls in these two quadrants, it will have an answer. And again, I'll explain that when we see those type of questions, but those are important notes to write. And then we'll go ahead and write this last one here before I need a new page. The inverse, again, will just switch the domain and range. Hopefully yours is a little bit more organized than what I've drawn here. But now this right here, sorry about that. So this right here would now be 0, and then, well, technically this goes, okay, so this would go -1, this would go 1, and then you would go from 0 to pi. So your function would look more or less I -1, and then 1, 0. So it'd be like this. So it's roughly something, not so curvy, something roughly like this, right? Where it's about to curve up and down. But that section would then pass the vertical line test. All right, let's look at the other trig functions because they want you to know all of them. So let's again analyze tan of x. We'll look at the domain. Tan of x, just like before, has a restriction already, and we'll look at that. It goes from negative pi halves to pi halves. Notice this time that these are parentheses and not brackets. Brackets is because they were included. Parentheses are not included because if you recall, these are asymptotes. So it's just going to be those sections of asymptotes, but then it shoots up like a cubic function, so the range was actually -infinity to infinity for that section. And again, to give you an idea, graph. Here's negative pi halves. Here's pi halves. So we had a function that kind of looked like this. So it had a restriction already, but couldn't cross it, and then infinitely just shot up. Well, the inverse would just switch the domain and range. And your graph now would look like where this is now negative pi halves. This is pi halves. But now we go from vertical asymptotes to horizontal asymptotes. I believe it does something like this. There we go. And then now has more of a cubic graph rather than a cubic graph. Well, how's that? Cube root graph versus a cubic graph. All right, and then and really personally in my experience, those are usually your three main ones that you deal with, but they do go into specifics on cosecant, secant, and cotangent. But again, when looking at those answers, we're going to probably be really analyzing how to evaluate versus how to graph those. But for sake of argument, we will discuss them. And again, also, I guess I need to write this as a note as well. Instead of it being written with this is the same thing. So like arc sine. So this would be the same thing as arc cosine. And if I kept on going, this would be the same thing as arc tangent. And so when I look at cosecant of x, We're going to give it a restriction as well. But remember, these are these quadratic functions. So it breaks up before it fails. So what we're going to say is we're actually going to go from negative pi halves, comma 0, and then 0 to pi halves as the domain. And then the range would then just be negative infinity to 1 union 1 to infinity. We can just kind of leave it there. I feel like you need a graph just to kind of see it. But cosecant, remember, goes like on the top of sines. So if this is pi halves here, and this is, we'll call this negative pi halves. If you recall, at 0, there's like a horizontal asymptote because sine is 0 at 0. So when you flip it, it becomes undefined. And then at pi halves, it hits a max. And then at a negative pi halves, it hits a min. So this is the part that you're actually graphing here. So this is its original graph, so that when we graph its inverse of that, which again would just be arc cosecant, we will have negative infinity to 1 union 1 to infinity. And then this would be negative pi halves, comma 0 union 0, comma pi halves. And I did not make that a bracket. This should be a bracket here. Bracket here. All right, so therefore the graph here, and I'll probably move on to a new section because it does take a lot of graph space. But now this is pi halves, and this is negative pi halves. And then this would be negative 1, and this would be 1. So what happens here is now we have a horizontal asymptote in which, man, if we flip this one, hold on. See, these again, I don't have too much experience with them because they're just not asked. Okay, so it's more like this. So like it starts here and then shoots in this direction. And then here you start here and then like go in this direction. So it's that infinite direction, these directions. And then the rest of them are kind of written that same way. So let's look at those last two, which would be secant. Oh, I don't know why I just put that in the middle. Your secant of x. And let's talk about the domain or the restriction that we'll have. It'll go from 0 to pi halves, union pi halves to 0. And then the range will go from negative infinity to negative 1, union 1 to infinity. And then the graph, to give you an idea of why we do this. So graph wise, I meant to write a pi there. Going back to 0 makes no sense. So here's pi halves, here's 0. If you recall that the secant is like there's the quadratics on top of the cosine function. So at pi halves, cosine was 0. So therefore we had an undefined statement. But we did have one here, and then it would go like this, and then we would have one here, and it would kind of go like this. So this is what we see with the secant graph. So when we look at the arc secant or the secant inverse, we're just going to flip the domain and range. and I don't know why I did that in the same color. I do apologize, but I'm not going to rewrite it. But this graph will go with this one. I'll put a red line here so you can see. All right, so this again now is pi, or I guess technically here, this would be 0, pi halves, and then this would be pi. And then we would go from -1 to 1. So at pi halves, this is now my horizontal asymptote. And again, trying my best here to graph this. The secant would go to that pi mark, and then it would kind of do this. And then here it would go to that 1 mark, and then it would do this. So that's kind of what the inverse of the secant would look like. And then, of course, the last one is the cotangent of x. Its restrictions are negative pi halves, comma 0. Again, notice just like with the tangent, they all get parentheses. Union 0 to pi halves. And then this would be -infinity to infinity. So to give you an idea there. On this one here, we actually have a vertical asymptote here. And then here's negative pi halves. And here is pi halves. So what they did here to kind of break it down is for the graph, it went down this way. So we have a graph that looks actually, I believe it would be this part here, like this, and then this one right here come like this. There you go. So you can kind of see the parts that they take from the cotangent. And then when we look at the arc cotangent or cotangent inverse, we, again, sorry for not changing that color. This is going to be -infinity to infinity. And then this would be negative pi halves, comma 0, union 0 to pi halves. So now I have this horizontal asymptote. Here is negative pi halves. Here is pi halves. And then here is -1. Here is +1. So what I'm looking at now is at that point here, it'd be an open circle, and I would go this way with it. And then here I'd go open circle, and then I would go this way with it. What makes this different from the tangent one is we actually, over here, we actually do have a value at negative pi halves and at pi halves. So therefore, this will actually be more like this. They'll actually have these solid and dotted guts right there. But because we're okay, but because we're trying to get in this restriction here, we will leave it as parentheses, even though it does have a value. We're gonna leave it as parentheses because it can't have a value at this point. All right, so a little bit weird there that this was only the one that we will include, which is kind of different from your code, from your tangent. All right, now on your homework, yes, you saw these graphs, but you don't have to graph any of these. You just have to find the correct answer. And a lot of times they want the exact answer. So the unit circle we built earlier in this chapter, or I think it was this chapter, earlier in this semester, you're going to be very useful to have. So let's do some practice with all that information. Let's look at number 1. It says sine inverse of -1 of -1. It says evaluate each following without using a calculator. So when you're asked for the inverse of a function, you are asked to basically say on the unit circle, where does sine equal -1, right? And when you do that, hopefully you're yelling two things. You're yelling, hey, it's going to be right here at either you're yelling at me at 3 pi halves, or you're saying at 270 degrees, right? For sake of doing most of this work, you're going to do the radiant answer only, unless it says degree. Now, on the flip side of this, when talking about the inverse, you are correct by saying 3 pi halves, but you have to remember the sine inverse is this right here, going from pi halves to negative pi halves. So even though 3 pi halves is the correct location on the graph, the answer, if you're below the x-axis, must be negative. So in this situation, the answer is negative pi halves. So again, if you get an answer somewhere in quadrant 3, you must turn it into a clockwise answer. If it lands in quadrant 1, we can take the answer as is. If it was to land somewhere in these two quadrants here, quadrant 2 or 3, this would be a situation where you say there's no answer. So let's look at a lot of others. Let's look at number 2. Let's say cosine inverse of the square root of 2 over 2. So again, on the unit circle, I'm asking, where does it equal the square root of 2 over 2? And hopefully you're saying it's here and it's here. Actually, I lied. Here and here, because this is where x is. All right, so here and here, right? And this one you would say is pi fourths, and this one here you would say is 7 pi fourths. All right, now here's the other issue that you have to remember. Cosine inverse is in quadrant 1 and 2. That's why I said this part's very important. So if it lands somewhere outside of quadrant 1 or 2, it cannot be an answer. Now, what's really nice about cosine is whatever the answer you get in quadrant 1 and 2 is the answer. You don't have to change it to its clockwise motion. So therefore, in this case, pi fourths would be the answer. All right, then we're going to look at number 3. And you're going to look at tan inverse. Oh, my bad. Tan inverse of 1 equals what? All right. So the best way I look at this is for tangent to equal 1, because you're, again, looking to figure out where tangent equals 1 at. It's got to be, remember, it's sine over cosine, but it's got to be, if this is 1, it means that sine equals cosine. And it only does that in 2 places. Here at pi fourths, and here at, what's that, 2, 3, 4, 5 pi fourths, because they'll both be negative. But for tangent, you got to remember as well that it was limited to just negative pi halves, or sorry, positive pi halves and negative pi halves. So therefore, it didn't fall in this range, so that would be out, and this would be the answer. So when you're looking at tangent of equal to 1, realize that sine and cosine have to be equal. And this coordinate here is the square root of 2 over 2, comma, the square root of 2 over 2, and that's where they're equal. So using that unit circle, we can quickly get our answers. All right? And that's the goal behind this. So let's look at number 5. Secant inverse of 2 square roots of 3 over 3. All right, on this one here, again, I'm looking to figure out where on the unit circle secant equals that. And you might be going, I have no idea. All right, now we know that secant equal to 2 square roots of 3 over 3 is got to be the same thing as 1 over cosine, which is 1 over 2 square roots of 3 over 3, which if we keep change flip this is now 3 over 2 square roots of 3. Rationalize it. It gives me 3 square roots of 3 over 2 times 3, so that cancels. So that gives me the square root of 3 over 2. Right? So it's a lot of work, but basically, if you see this, know that it equals this for the cosine part of it. All right, so for cosine's sake, cosine falls in the inverse world, just like secant does, falls in the first two quadrants. Square root of 3 over 2 is larger than the other fraction you have to remember, which is 1/2. And therefore, I must be closer to the x-axis. Because remember, we're labeling this as cosine comma sine. So cosine must be my sine value. So if I'm closer here, then you got to know your three basic ones: pi 6, pi 4, pi thirds. So at pi 6, I must be the square root 3 over 2. And then it's going to also be the same thing as 11 pi over 6. But again, for secant, it only happens in the first two quadrants. So therefore, we cannot pay attention to this, and pi 6 would be my answer. Okay? So again, this is just a memorization thing, but if you see this, know that's the same thing as cosine. But if you don't, I kind of had the idea, but I didn't want to be wrong about it. So, but showing that process, you can always come to the conclusion. So it's not always about memorization. You can always calculate the answer too, when in doubt. All right, let's look at one more of these types. So we'll look at number 7. This says arc sine of 0. So remember, that's the same thing as sine inverse. So where on the unit circle does sine equal 0? And hopefully, again, you yell at the computer saying here and here, which is at 0 and at pi. And then remember that sine inverse falls in between quadrant 1 and 4. So that one can't be the answer. So the answer must be 0 in itself. All right, so let's look at some different type of questions you'll see. Let's look at number 26. 26 says evaluate each of the following expressions, if possible, using a calculator and round in your answers. All right, so here we go. So you're asked to find cosine -1 of 4. Here is the issue that you have to figure out. Obviously, I don't know where 4 falls, but you have to know, is 4 in between 0 and pi? Well, you might not know all your measurements, but you should know around about that pi is 3.14. 4 does not fall between these two numbers. So because of that, we cannot physically type this into the calculator and get an answer. So therefore, this is what we call does not exist, which I believe is what they tell you to label. Now, on the flip side of this, had you not realized that you could have typed it into the calculator, it would have said the same thing. It would have said like error or doesn't exist or out of domain or something like that, which would have been your indicator. The issue is a lot of students might type it in and have the wrong mode on, or they'll type it incorrectly and think they're typing it incorrectly and get the wrong answer and go, oh, it must not be correct. So it's always just good to know, does it fall between this and what kind of answer should I get? So in this case, this would be a does not exist. All right, let's look at a different type of question. Let's look at number 32. Again, use the formulas, and they give you a whole bunch of different formulas above to evaluate each of the following expressions, if possible, using a calculator. Round your answers to the 4 decimal places. Okay, so we get secant inverse of -0.5. Remember, secant is cosine, so it has to be in this range right here. So what we're going to do is we got to go, all right, same concept, just with a secant rather than a cosine. Does -0.5 fall between 0 and pi? And actually, I should be these little markers here because it can hit 0 and pi. And hopefully you're going, well, it's a negative. Obviously, it can't. And you're correct. This would be a does not exist. That part right there does not fall into the domain. So therefore, you cannot find an original answer. So this, again, that's where that domain and range does come into play, and you want to focus on what quadrant can it fall in. All right, let's look at some different type of questions. Let's look at number 37. 37 says cosine inverse of cosine of 2 pi force. Okay, no, with all the parentheses. All right, so a lot of students will get this wrong in the sense that they'll go, all right, well, an inverse of original function must cancel out. That must be the answer. That can be true, yes, but it's not always true. You got to see where does this fall. So I'm going to rewrite this function as cosine inverse of cosine pi halves. And this is like a composite function. You got to work inside out. So you got to figure out what is cosine of pi halves. Okay, so that's what we'll do first. Cosine of pi halves, that's right here, is 0. Now we can go, all right, where on the unit circle does cosine equal 0? And it has to fall between the quadrants 1 and 2. And in this situation, that happens to also be pi halves. So in this case, yes, the two did look like they canceled each other out, but that's not always the case because there are some times when you work this answer out, you land somewhere over here, but then when you're asked the question, you can actually land up here and you'll get a totally different answer. So we'll do some like that. Let's look at number 38. So this one is sine inverse of sine 3 pi halves. All right, so once again, I'm going to do the inside first. Sine 3 pi halves. All right, so that's 1, 2, 3. 3 pi halves. All right, so sine 3 pi halves would be -1. All right, now I'm like, all right, where does sine equal -1? Well, it's right here. But remember, sine goes from pi halves to negative pi halves. So even though 3 pi halves is the correct location on a graph, the answer has to be between pi halves and negative pi halves. So this answer is actually negative pi halves, not 3 pi over 2. So notice that they didn't just simply cancel and you're left with that answer. In this situation, you were given a different answer, landed in the same spot, but represented differently. All right. So let's do some others. Let's look at number 43. It says sine arc tan 0.4. Right, and in this situation, it says evaluate each of the following expressions if possible, use a calculator. All right, so first step, we need to figure out arc tan of 0.4. So tangent falls between first quadrant and third quadrant. Okay, so that means does 0.4 fall between pi halves and negative pi halves according to our domain restriction? Actually, I completely lied. That would be the restriction of regular tangent. With arc tangent, it actually goes negative infinity to infinity. I forget that tangent's different. All right, so arc tangent's domain is negative infinity to infinity. So therefore, this one will have an answer no matter what. All right. The only issue is I got to figure out like what the value is, because then sine also has a domain to give us infinitely many answers as well. All right, so okay, so thinking about this. All right, so again, arctangent's domain is negative infinity to infinity. So this answer can be whatever. And then if you just look at sine itself and don't think about the inverse, sine's domain is also negative infinity to infinity. as a full. So no matter what the answer inside of arctan is, I can get an answer out. And no matter what that answer is, I can get an answer out of sine. So when that happens, I can just type this straight into the calculator because we don't have a place where that equals 0.4. So what we're going to do is we'll look at a calculator. Make sure I'm sharing the right one here. Perfect. All right. So to type in that question, this would be, you can go to the trig function and you would type sine and then back to the trig function, tan inverse 0.4. And I want this to be in radians. So if my calculator is in degrees, I'm just going to simply click it and it changes it to radians. I can then now hit the answer or hit enter and I get my answer. So in this case, round to 4 decimal places, this will be 0.3714. So I come back over here, my answer is 0.3714. All right, let's look at another one. Let's look at number 44. This one says sine inverse of cosine 3 pi halves. All right, 3 pi halves, 0. So remember, we go inside out. So here's 3 pi halves. Which would be for cosine, it's 0. So this is sine inverse of 0. So then the question is, where does sine equal 0? Well, sine equals 0 here and here, but sine inverse falls between here and here. So therefore, this one's my answer, and that happens to be 0 in itself. So we didn't even need a calculator. I'm going to square so it doesn't look like a donut. But 0 would be the answer. All right, the next question, it's very similar to this one, number 50. And it says, again, without using a calculator. So let's look at this. So this is going to be cosine secant inverse of -2. All right, so secant, I'm basically trying to figure out where does secant equal -2. So if you don't remember, we can kind of go through here. Secant equals -2, which would be the same thing as 1 over cosine. So in this case, that's 1 over -2. So therefore, that would be the same thing as asking, what is cosine of -1/2? So in this case here, we can say cosine equals -1/2 right here. Actually, cosine equals -1/2 here and here. All right. So that would be at negative pi halves, or -1/2. That would be that'd be 2 pi thirds here, and then this would be 3. This would be 4 pi thirds here. All right. And so we're looking at this, and we're like, all right, that's where secant is equal to that. However, secant is just like cosine, is restricted to the first 2 quadrants. So therefore, the answer must be 2 pi thirds. So here we go. Now the question is, what is cosine of 2 pi thirds? And for cosine of -2 pi thirds, the answer would be, well, you did the pre-work over here, would just be -1/2. All right. So that's kind of work there. Let's look at some others to make sure we fully got an answer. Let's look at number 67. It says express each of the following functions as a purely algebraic function. So it tells us we have tan of cosine inverse of x. All righty. Okay, so let's build a triangle, I guess, in this situation. Because we don't have x on the unit circle, we can just say, all right, cosine inverse of x. Let's call this theta. So that would be our opposite. This would be our adjacent, and this would be our hypotenuse. Just trying to label our stuff. Cosine, remember, is ca, so that's adjacent over hypotenuse. And if we have x, then that would mean that adjacent would be x, and my hypotenuse would be 1. Okay, so that would be cosine of x. So where does cosine equal x over 1? So I know that this is my adjacent, this is my 1. I just don't know that yet. So what we can do is we can calculate this opposite by using the Pythagorean theorem. So that'd be x squared plus, I'm just going to call it b, doesn't really matter what you call it. And then this would just be b squared equals 1 minus x squared if I just subtract the x squared over. And then b would equal the square root of 1 minus x squared. So there is my opposite. So now that I use the inside information to build the triangle, now my real question is, what's tangent of this triangle? So tangent is TOA. So that would mean that that's going to be opposite. So that's square root of 1 minus x squared divided by TOA, so adjacent. So that'd be x. So in this situation, my answer is 1 minus x squared over x. So this is the process you would go through if you're presented this question, and trust me, you will be. So let's do this about 3 more times. Let's look at number 68. It says cotangent of sine inverse 2 over x. So same process. SOA for sine. All right, this is my opposite. This would be my hypotenuse, and this would be the adjacent. So my opposite is 2, and my hypotenuse is x. So let's work this out. This becomes 2 squared plus b squared equals x squared. So b squared equals x squared minus 4. So b equals the square root of x squared minus 4. All right, and then cotangent is, if tangent is TOA, then cotangent would be CAO. So it just flips. So therefore, that would be adjacent. So the square root of x squared minus 4 divided by the opposite, which is 2. There you go. Let's do a couple more. So the number 69 is secant of tan inverse of 3x. Same process. Let's build a triangle. This is my opposite. It doesn't matter how you live. You can put it here. You still get the same outcome. Tangent, again, is TOA. So opposite would be 3x. Adjacent would be 1. Let's calculate our answer. 1 squared plus 3x squared, that'd be in parentheses, equals, we'll call it c squared. This is 1 plus 9x squared equals c squared. So then the square root of 1 plus 9x squared equals c. And then secant is the opposite of cosine, and cosines, so TOA. So that means secant would be equal to hypotenuse over adjacent. So that would mean then we have 1 plus 9x squared divided by 1, which in this case can just be written as 1 plus 9x squared. Yep. All right, last one. We should have enough examples for your homework. So number 70 says tangent is equal to sine inverse of x over the square root of x squared plus 3. Keeping with it, just because it got bigger doesn't matter. All right, so this would be sine is so that's my opposite is x. My hypotenuse is the square root of x squared plus 3. And then I got to calculate the adjacent. So here we go. So x squared plus b squared equals the square root of x squared plus 3 squared. So that gives me x squared plus b squared. Those would cancel. X squared plus 3. Subtract x squared. Those cancel. So I get b squared equals 3. So b equals the square root of 3. Okay. Tangent then is TOA. So this would be x over the square root of 3. Are they going to make you want to go? Then you got to rationalize that. So you want to multiply the top and bottom by the square root of 3. So you get the square root of 3x over 3. Had this been just a paper test, I probably would have accepted this. But since it's a online course, this is what they are looking for. All right, that seems to be all that I have. So if you need any more examples or any more help, just reach out. Until the next video. Bye.